Okay, this video is going to serve a couple different purposes. One, it'll be a review of the things that you hopefully learned in statistics for the behavioral sciences. You know, we talked about correlations, regressions, independent samples, t-tests, ANOVAs. Just FYI, a lot of people don't get it the first time you go through a stats course. When I did an undergraduate stats course, I don't think I learned anything. I took 2 or 3 graduate stats courses, and I didn't really remember that much from those either. It was through actually doing experiments and collecting my own data and doing the analyses that way is how I learned how to do stats. And then I learned a lot by teaching stats. That's what really helped. So it's like, if you don't remember a lot from the intro stats class, don't worry. That's pretty common. That's pretty normal. In any case, so part 1, it's a review of the things that we learned in that course. The other part is that I want to start exposing you to R. For the intro class, you probably used Excel, maybe SPSS. When we start doing these more advanced statistical analyses, we should probably do it in R for various reasons. One big reason that a lot of people will mention is the idea that SPSS costs money, and so once you graduate, you would either have to get a license for SPSS, but with R, it's free. So you can use R Studio. I'm going to show you in Google Colab today. And so the link for this exact sheet that I'm going to be using, I'll post it in the comments so that you can just pull this right up and you can use it anytime you want. And I'll also post this other document with the APA write-ups too, so you can pull these up. Okay, in Google Colab, when you're in here, one thing you do have to do at first is make sure you're in the right environment. So if you go down here into this corner, it says runtime options, click there. I think the default is to be in Python, so just make sure that you are in R. On the first part for R, I've loaded a whole bunch of packages, and so each one of these, you press Shift and Enter to install it. I've installed a bunch of different things, and these are used in the different, like ANOVAs for that one, and so we'll go through that, but this is to make plots. Each one of these, Shift Enter, it may take a while to get them all loaded up and ready to go. Typically, you wouldn't be doing all these analyses though at one time. So in any case, you install all those packages and then you basically load those. And so if you press Shift Enter on these libraries, it's going to like load those different packages that we put in. Okay, for the first one, I have all of my data sets for this at GitHub. I think it's in one called like Bradley Stats Course, something like that. And so what this is doing is this is going to load the data we're going to do a correlation and a simple regression here. This DF, you'll see that a lot. It means data frame. And so we are reading this CSV from this website, GitHub, and it's going to load it into this data frame that we're going to call DF. And again, you just press Shift, Enter, and now it's loaded that up. While we're here, let's go ahead and if you put DF after you've loaded that up and you just press Shift Enter on that, it's going to show you what the data frame is, what your data is. And we'll see this is from one of the textbooks we use. It was about cards sent and cards received. Is there a correlation between those two things? And so somebody sent 5 cards and they received 10 cards. Back to the brief review for this stuff. Correlation, we're looking to see if there's a relationship between 2 variables. And so in this case, is there a relationship between sent and received? So we have this data frame pulled up. This is to do the correlation test, cor.test. And we're going to be looking at our data frame sent and the data from our data frame for received, the method, which kind of correlation are we going to be doing? We're going to be doing a Pearson's, and this COR test, that's just the name that we're giving it. You can call it anything you want. And then also, it looks like we are going to get the components. So R, the P value, the T. And so let me go back to this here. At least for the correlation, for what I have from our textbook, we are looking for the R, Pearson's R. We are looking for the degrees of freedom, and we are looking for the P value. And so, yeah, if we have this, again, we're doing that correlation, cor.test. If you had different variables, you would call them, DF, $, and whatever your variable is. So yeah, we just go there, Shift Enter. It gives us our Pearson's R that we're looking for, 0.8. P-value is 0.10. Degrees of freedom is 3. For correlation, it's going to be n minus 2. And we have 5. You can see 1, 2, 3, 4, 5. There's 2 of those, or one number from each column that's not free to vary. So n minus 2 gives us the 3. Our T statistic is at 2.3. 0.31. Pretty high R, but it's not significant. And, we've talked about this. In the first class, at least when I teach it, I talk about this a lot. Your sample size matters, and our sample size is pretty small. So it's possible to have a really big R, but not a very small P, which is what you're looking for to find significance. Also, I guess as a review, when we talk about significance, we're talking about P being less than 0.05 typically in psych science studies. Our P is not less than 0.05, it is 0.10, so this would not be significant. Related to the correlation, a simple regression, basically we're just saying that one variable is going to predict another variable. For the correlation, we're saying that there's two variables and there's a relationship. But with the simple regression, we are saying that one variable actually predicts the other one. We can call it a predictor variable. I think in SPSS it's called an independent factor. I don't like it because it confuses people when you call it independent, but I think a predictor is a pretty good term for it. And so, yeah, here we go. We're using the same data set for this. So what we're going to say here is that cards sent predicts cards received. And if you want to go back to the materials from last semester, we go way in depth into all the mathematics behind that, but that's not what the purpose is today. Just a review and to get you familiar with R. I'm not going super in depth into all these different commands, but we will go a little bit more in depth into those in another class. But for this, so when you have a hashtag there and then you have a comment, so this isn't actually code that we're running. It's just basically telling you what we're doing there. So if you have a little hashtag and then whatever your comment is, and it's good like code hygiene to put things in like that so that people know what's going on if they were to look at it. Model, that's what we're calling this. We could call it anything we wanted to, and then those symbols here, and then LM, linear model, cards sent is going to predict cards received. And the data that we're using, DF, that data frame that we had created earlier. If we just ran that part, it would not give you any output. What you want to do is a summary of that model, MODEL, that we just did. Shift enter. This is the output from SPSS for that first analysis, the correlation. And so the 0.80, the p-value, you're probably used to seeing this output here. And so you would just basically, you can see that what we get in R is exactly the same. It's just the output just looks a little bit different. The 0.8 is right there. The 0.10 from SPSS, 0.10 is right there. And then the N of 5, again, the degrees of freedom, 5 minus 2. And so in SPSS, if we have the predictor of sent to do the linear regression, where one variable is predicting the other, so we are saying that cards sent is predicting cards received from our DF, our data frame. In SPSS, this is what that looks like. So we had a R squared of 0.64, that 64% of the variance in cards received can be predicted by cards sent. R ANOVA, degrees of freedom, are that 1 and the 3. Our F statistic and our p-value, still not significant. And then our coefficients, it's going to be the same as the correlation when you just have one variable that you're looking at. So for each increase in cards sent, cards received goes up by 0.80. That's what it looks like in SPSS. In R, do that Shift R, or Shift Enter, sorry. Exact same thing here. So degrees of freedom, 1 and 3, right? So here's this right here. 1 and 3 for degrees of freedom. The F statistic, 5.33. P-value still 1.04. F, 1 and 3, 5.33. 0.10. Our R squared, we get it from right there, 0.64. When you report it, it's 0.64. It doesn't have a leading 0 because it can't go over 1. Our beta, our T, and our P are all right here. So cards sent, the unstandardized beta is 0.80. Our T value is 2.3, and that P value again is 0.104. Pretty much the same for a multiple regression. So simple regression, it's one variable that is predicting one other variable. Multiple regression, we have multiple variables that are predicting one variable. The data for this one I got from Andy Field's textbook, Discovering SPSS. I pulled up this data with this command here, Shift Enter, and then so you can put DF, and it'll list the entire data frame. If you just put head in parentheses DF, it'll give you just the first 6. What this is, this data set, is its album sales in hundreds of thousands, so 330,000 for sales. And we have 3 predictors. Adverts, like how many advertisements they had the week before the record came out. I mean, this is kind of antiquated. We don't do that anymore, but let's pretend. So advertisements for this album that was coming out, how much they played it on the radio, again, antiquated, how much they played it on the radio the week before, and image, what the band looks like. You'll notice that these are all completely different scales. So advertisements, these are in hundreds of thousands too. So they spent, 985,000, 574,000 they spent on advertisements. Airplay, they played it 44 times that week before. The band image, I believe it's on scale from 1 to 10. So they got a 5 right in the middle. That's our data set. In this here, we're going to run the regression model. And so same thing, model, linear model. And what we are doing is we are predicting sales by adverts, airplay, and image. The data again from DF. If you have different variables, you can see to replace the Y with whatever yours is. Ours is sales, and then X1, X2, X3. You can put as many as you want, and it's just whatever that actual column name is. Shift Enter. Again, it doesn't actually do any output, and so you want to do a summary of the model. So Shift Enter on that. Back how we're going to report this. We do have our degrees of freedom, the 3, and from the, let me show you SPSS real quick. From SPSS, when we run this, our ANOVA, the 3 and the 196, our F is 129.50, our R squared from right there, 0.67. Our different coefficients, we have unstandardized and we also have the standardized. I'll talk a little bit more about that in a second. All of this information is the exact same information that's here. It's just a little bit more, some people would call it maybe a little bit more user-friendly in SPSS because it is, point and click. It's not as, this looks more like code than it does like this kind of more pretty output that you get from SPSS. In any case, our F, our degrees of freedom right here, 3 and 196. Our F statistic, 129.50. Our p-value, so you might see a number like this, a 2.2 exponent negative 16. Basically what's that saying is that you have to move the decimal place over 16 times. What that means, it's a negative 16. So the p-value is really, really small on this. We do have a significant finding here. So I would write this up as, when you see a number like this, p less than 0.001. Our R squared, again, 0.66. That's our R squared. On our coefficients in SPSS, this is what those looked like right here. So as adverts goes up by 1, sales went up by 0.085. As airplay goes up by 1, sales goes up by 3.3. Image, as it goes up by 1, sales go up by 11.09. All of these are significant, so there's our t values for each one of those. Significant, all less than p, less than 0.001. Exact same thing here in R, the exact same numbers, and we would just report each one of those. For this, because they are all on different scales, maybe you report the unstandardized, maybe you'd also report the standardized, because it's like when you see image and it's at 11, it's like, okay, well, that's the biggest predictor, but it's not, because the scale was from 1 to 10 when sales, that scale was from 1 to, I don't remember, 1 million, because image is actually the least of the significant. Now, to do that, to get those standardized, you do have to do it slightly different. We are going to standardize the variables. So right here, you can see that. So data frame, we are putting them all on the same scale, basically z-scoring everything. So it's on the same scale. Z-scores, like if you had ACT scores and SAT scores and you wanted to compare them, you can put them on the same scale, essentially. You z-score. So we're putting it on the same scale, and then we are going to run that model again. Shift Enter. And so now we can see our coefficients as standardized. Again, we are dealing with the exponents here. So an exponent of -1, if it's 5.1, you would just move it over 1. So 0.51. As adverts goes up by 1, sales goes up by 0.51. This is going to be confusing for some people to have to do that mentally in your head. So I have put it together where we take that model summary of those coefficients and we round them. So you actually see what the numbers are instead of seeing the exponents. That's what this part is here. We can also put it all together so that you can see it. And so this is the p-values, and this is where we're putting it all together. And then that's doing the results. And so if you do that, adverts, for each increase in adverts, sales goes up by 0.51. It's the exact same thing here. It's just, again, you have to do something in your head to get that, to move that decimal place over. And this is maybe a little bit cleaner for some people. Okay, that's the correlations, the simple regressions, the multiple regression. The rest of the intro course, statistics and behavioral sciences, We talked about independent samples t-test, paired samples, one-way ANOVA, repeated measures ANOVA, and a two-way ANOVA. One sample t-test is also. So there was 3 t-tests and 3 ANOVAs. With the one sample t-test, you are comparing a number that you have to a hypothesized population mean. So maybe you don't actually know what the mean is. You're making a guess. What we need to report is the mean, standard deviation, maybe the confidence intervals, the t-test, the degrees of freedom for that, and what the t statistic is. Our p-value, maybe Cohen's d as well. So you can see all that right there. As an example, like if we went to a daycare and we think that maybe the average age is 2, but we don't know. We're guessing. It's a hypothesized population mean. So if the average age is 2, we go into the daycare, we go to the classroom, and we find 3 kids there, and one is age 1, one's age 3, and one's age 5. So we got 3 kids, 1, 3, and 5. That's our data. On most of these, I just pull up data from GitHub. This is how you would actually create a data set if you wanted to. I'm creating a data set called age. And then with this, it's basically saying we're doing something here. And that C means create. And then in parentheses, you'd have your data set. And so I could put comma and I could put in more data if I had it. That creates that data set. And then to run the actual one sample t-test, we have the t-test, which is going to be age as our variable. And what we're looking for here is whatever our test variable is. If you remember in SPSS, you had to put in a test variable. And if you didn't, if you just left it at 0, it was going to compare it to 0, which a lot of times gave you a vastly different number than whatever the actual test value was. You can see it here in SPSS, test value 2. And so yeah, we can, our mean was 3. So we're comparing 3 to 2. There's a mean difference of 1. You see it right there. Our confidence intervals, and then our Cohen's d is at 2. Our Cohen's d is at 0.50, and our standard deviations there also, which are all the things that we are going to report. In R, shift enter on that, we get our degrees of freedom 2. We get our t statistic is a 0.86, pretty low. Our degrees of freedom 2, p-value 0.47. So it's pretty far from being significant. Our confidence intervals are listed right there, and the sample estimates, our mean was a 3. For ours. So we were comparing 3 to 2. Those libraries that we loaded up earlier, you have to have those loaded up to do things like this, the Cohen's d. And so d out, that is what we are creating, where we're doing Cohen's d for the age, the hypothesized mean of 2, one sample, true, and then print that variable that we just created, d out, shift enter, 0.50, which is exactly what it was in SPSS. And that's like the piecemeal, how you go through each step of it. You can't actually put all this together and it'll pop it all out in APA style where you just copy it right over. So in this first part, we're creating the data set. In the second part, we are running that one sample t-test. In the third part, we are computing Cohen's d right there. In this part, we are going to extract all of those different values. So we get our mean, our standard deviation, all the things that we need to report in APA style. Our mean, standard deviation, the value of t, our degrees of freedom, our p-value, our confidence intervals, and that Cohen's d. That's what all of that is there. And then this prints all of that. You don't necessarily need to know exactly all those numbers right now, what that means. But for example, so that percent period 2f, it's basically saying we're going to round it to 2 decimal places. Yeah, if we click shift enter, ta-da. Exactly what we need for over here to report that in APA style. Our mean 3, standard deviation 2, our confidence intervals at -2, basically to about 8. T, degrees of freedom 2. T value, the value for it 0.87. Our P, again, almost 0.5. And then Cohen's d, 0.50. For some people, they consider R to be more difficult than SPSS because SPSS point and click. But it's like, if you have all this loaded up and you have the data set, I mean, it's just shift enter. If you have, exactly what I have here, and you can just copy this over and you can just do it over and over again, and it just pops everything out perfectly. You don't even have to search through the outputs. It's like for some people, R is actually easier than SPSS. All right, so that's one sample t-test where you're comparing your sample that you got to a hypothesized population mean with an independent samples t-test. You'll sometimes see it also as a 2 sample t-test. It's 2 different samples that are independent of each other. So it's 2 different groups of people. You're not in group 1 and in group 2, you are in 2 different conditions. If we were going to run like a medication study, one group would be the placebo or the control group, and one group would get this drug, and we would see if there's a difference between the 2. Independent samples t-test. It was created to make Guinness beer better. It's an interesting story if you want to look into that. In any case, this first step, we're loading that data, and then that head df is going to show you what the data frame looks like. And it looks like I did group and prejudice. I believe that this data was mortality salience. One group we were reminded of their mortality, one group we did not. And then we did some measure of how prejudiced they were after that, because mortality salience typically increases things like intergroup bias. So we pulled that up. Now we're going to run that independent samples t-test. Some people have moved from independent samples t-test. They would rather run the Welch's t-test, and you can do that here too. The only difference is, so right here, t-test or t-result. This is the thing that we're creating by running the t-test with prejudice, using that factor of group, our data from that DF data frame, variance, VAR period equals true. That's for the independent samples t-test. If you want to run the Welch's t-test, you just take that last part off and it'll run it. Okay, shift enter, view the results, shift enter. From SPSS, we can see that we do have a significant finding. So the P is less than 0.001. The means for group 1 is 3.1, mean for group 2, 5.1. So there's a mean difference of 2. It says that somewhere in this there. Our confidence intervals, about a -3 to -1. So it does not overlap with 0, suggesting that it's probably going to be significant. And our Cohen's D, it's pretty large, 2.01. That's big. That's what it looks like in SPSS. What we are trying to report here, the mean for each group, the standard deviation for each group, the T, the degrees of freedom, the T statistic, the p-value, confidence intervals for the mean difference, and then Cohen's D. We get a lot of that information just by looking at that results for the 2-sample independent samples t-test. RT, -4, degrees of freedom, 18, p-value less than 0.001. Our confidence intervals, just like in SPSS, about a -3 to -1, 3.1 compared to 5.1. That gives us the majority of the information we need. Get Cohen's D, another D result statement. We're taking Cohen's D, prejudice group, print that out, just like in SPSS, -2.01. And like with the other one, that's how you go through each step. If you want to load the data, run the independent samples t-test, look at the results, compute Cohen's D, and that gives you all the information that you need to report it in APA style. You can also put all that stuff together, which I've done with this. That's a lot of information there, but you're getting the group means and the standard deviations with this part. We are getting our t-value on step, it's called 4, but it doesn't matter. The t-value, our degrees of freedom, P, confidence intervals, and our Cohen's D, and then this is actually printing all of that information out. Shift enter, and there we go. It's like, it's perfect. Group 1, the mean 3.1, standard deviation. Group 2 is 5.1, standard deviation. Our t-test 4.50, p less than 0.001, confidence intervals, Cohen's D. I mean, it's perfect, just ready to go, and you can write it up. Independent samples t-tests, it's 2 different groups of people. The next one we learned about in the other course was the paired samples t-test, and this is where the 2 groups, or the 2 different variables that you have, are actually connected. It's essentially, it's the same people, and you're running them through the condition twice. The easiest way to think about it is a pre-test, post-test. So you have the pre-test, and then maybe you do something, some kind of intervention, and then you have the post-test to see if there's a difference between pre-test and post-test. Okay, so step 1, again, just like all the other times, we're pulling up the data, we're calling it something. I call it DF. Maybe you check to make sure that it's actually there. So that head DF, and we have anxiety 1 and anxiety 2. So anxiety 1, maybe we just get a baseline, and then maybe we give them something, an anti-anxiety medication, and then we do anxiety 2 to see if that medication actually caused anxiety to go down. This is what we are looking to get out of our paired samples t-tests, the means for both, the standard deviations for both, the mean difference. It's just like the independent samples. Our confidence intervals, our T and our P and our D. Okay, so we got the data frame loaded up. In SPSS, this is what this looked like, the paired samples t-test. We got our means, standard deviation. So for anxiety 1, for anxiety 2, our paired samples t-test, it is going to be significant. Let's say we're doing two-tail. P less than 0.05, and we got a P of 0.047. So we do have a significant finding. Our T, our degrees of freedom, all in there. And then Cohen's D in this effect size. So anxiety 1, to Cohen's d, the point estimate, 0.563. Okay, so in R means, standard deviations, you can get that for both. So the mean for anxiety 1 was a 5.2. The mean for anxiety 2 is a 3.93. So now we do a t-test with, from our data frame, anxiety 1 and anxiety 2 paired, meaning are we doing a paired samples t-test? True, we are. So shift enter, and you get most of the information you need there. Our t statistic, our degrees of freedom, p, just like an SPSS, just barely under that 0.05. Our confidence intervals totally makes sense, a 0.02 to 2.5, so it's like they don't overlap with 0, but it was super close, and that's why it's just barely significant. It's just barely less than 0.05, let's say it that way. And yeah, the mean difference between 5.2 and 3.9 is 1.26. Get that, get our Cohen's d, just like with the other ones, shift enter, 0.56, just like in SPSS. And that's how you do each step. If you want to put it all together to have that nice clean output in SPSS, it looks the same. We're getting means, standard deviations, we're getting our t, degrees of freedom, p, confidence intervals, and the d, and then this statement here prints all that out. Now, if you were actually writing it up, so I put that in there, anxiety scores decrease from time 1 to time 2. If you were doing something different, you would want to make sure to change that wording and not just copy and paste that over. But for this, anxiety scores decrease from time 1, our mean standard deviation, to time 2, our t, our p, our confidence intervals, and the Cohen's d. I mean, it's perfect. You can just take this and copy and paste it over. I mean, it's done. It's perfect. Except for there's one small thing you would want to do for APA style. Is several of these things would need to be in italics, and we could actually get it to do that in R. I haven't done it right now, but it would be easy to fix. I'll go in and after this video is done, I'll go in and change that so it does do those. The M, the SD, the T, the P, and the D. They should all be in italics. Independent sample. So one sample is t-test, independent samples, paired samples, and then in the other class we started doing ANOVAs. The first one, the easiest one, the one-way ANOVA. Whenever you're doing an ANOVA, it just means that you have more than 2 groups. So the easiest one's the one-factor ANOVA. You have one IV. It could have as many levels as you want. In this example, it's just going to have 3. But if you have more than 2 means, you got to do an ANOVA. Let's see what this is. Okay, degree. Print this out. Group 2 in therapy. So they've done some kind of, there was 3 different groups. So, okay, let me back up. Head, DF, it just gives you those first 6. If you need to see all of it, because it's like, okay, how many groups are there? If you do DF, it'll show you all of the data, and we have 3 different groups. So group 2, 1, 2, and 3. They did different types of therapy. I don't remember what it was. Maybe there's a control group, maybe there's CBT, and maybe there's exercise, or whatever it is. For, let's say we're doing mild depression. And then the therapy, it's like whatever they were measuring, depression or anxiety, where they're at after this therapy. Okay, so when we do this, we also have to do one other thing, is we have to, so we see it as 1, 2, and 3, and we know that like in SPSS, when you do that, you call it a factor. Also with the independent samples t-test, you have to tell SPSS that group 1 is 1, group 2 is 2, and you also have to tell SPSS that 1, 2, and 3 is a factor. They're different grouping types. We have to do the same thing in R. So we're going to convert that group 2, is what the variable is called, to a factor so that R knows that we're dealing with 3 different groups. We can look at the means, standard deviations first if we wanted to. So for group 1, the mean, let's say it's anxiety, 5.3. For group 2, it's 4.3, and for group 3, it's 4. So it's going down. Are there significant differences? We don't know. This is just the mean standard deviations. To run an ANOVA result, you can call that whatever you want. And then we are doing AOV, is to do the ANOVA, and it's therapy by the factor of group. And we're using our DF data frame. And then the summary actually shows us the results. If we look at those results in SPSS for comparison, there was our mean standard deviations. So the 5.3, the 4.3, and the 4, you can see those. And then the ANOVA, degrees of freedom 2 and 27, are F 2.0. It is not significant. We do not have a significant ANOVA. We see the exact same thing right there. So degrees of freedom 2 and 27 are F 2.0, and our P is 0.15. Not significant, but let's say we did have a significant one and we want to do some other things. Maybe you want to get your eta squared. if we go back to the write-ups, what we're looking for here is several things. We want to get our means and standard deviations. We want to get the ANOVA, the F, the P, and the eta squared. To get that, eta squared, get that. And so shift enter, and then eta squared right there, 0.13. Additionally, and so if we go over here to the write-ups, we would get our mean standard deviations, the ANOVA, eta squared, and then we'd also do some post hocs. You do Tukey's or Bonferronis to see which pairings are significantly different. So we have 3 different groups. It's like, is 1 to 2 significantly different, or 1 to 3, or 2 to 3? You can just do Tukey on a significant difference, and then from that ANOVA result that we had created. And you can see 2 to 1, none of them are significant. So the P value is on the end here, 0.36, 0.14, and 0.87. And it gives you the mean difference at first. So 2 minus 1, 3 minus 1, and 3 minus 2. If we did have a significant finding, and maybe for whatever reason you don't like Tukey's, you prefer Bonferronis, this is how you would do that. A pairwise t-test with our variables of therapy by group, and then that P adjustment using Bonferroni. Shift enter, and there you go. So this is just giving you the P value, 1 to 2, and 2 to 3, and 3 to 2. 1 to 2, 2 to 3, and 1 to 3. You can also, if you want to, do your figures in, I just thought I'd use this as an example, you can do your figures in R using this here, ggplot. And so I'm not going to go super in depth into this, but what this is going to give us is, let's just run it, shift enter. Our groups are at the bottom here, 1, 2, and 3, and then our therapy score along the side. If remember, it's like 5.3 and 4.3 and 4. This is using the standard error, which is fine. Some people like to use the confidence intervals, and so I've also included that as well. And so if we click shift enter, a lot of overlap between these confidence intervals. We did not have a significant ANOVA, nor did we have significant pairwise comparisons in those confidence intervals. Lots of overlap there. That is going through it in each individual step. Can we put it all together and have it reported really nice and clean in APA style? Yes, we can. This first part's getting our effect size. The next part is getting our F value, degrees of freedom, our P value, our means and standard deviations, and then this is creating all of that in APA style, and then this is going to print that out. Oops, not quite in the right place. There we go. Shift enter. There was not. So you got to change it for each time. There was not a significant. If there wasn't, you might just put P less than 0.05 and stop right there. But there was not a significant effect on group on therapy outcomes. Our F, the degrees of freedom, 2 and 27, our F statistic, P value, eta squared, and then our means and standard deviations. And then we could, if we wanted to, maybe I'll go back later on and do this, add those pairwise comparisons in there too. All right, moving right along. So we had the one-way ANOVA, with the one-way ANOVA, it's 3 different groups, and each person, they're independent of each other. You're in group 1 or group 2 or group 3, you're not in M1 and 2. With the repeated measures ANOVA, it's the same person that's being run through multiple conditions. So it's like the paired samples, but instead of having just 2, we have 3 or more. So maybe time period 1, time period 2, time period 3. Let's pull this up, see what we have. This is anxiety 1, anxiety 2, and anxiety 3. So maybe they've gone to therapy for a month, and then for 2 months, and then for 3 months. And in each one of those months, you get a measurement of their anxiety, the DV. So anxiety 1, 2, and 3. This is how we would have that set up in SPSS. We would have our subject number, participant number, however you want to put that, and then anxiety 1 at each column. Anxiety 1, anxiety 2, anxiety 3. R doesn't like it like that. So what we need to do is kind of change how it is, and we need to put each participant is going to, each one of those DVs is going to be in a unique row instead of in a unique column. Before we do that, we can get the mean standard deviation, just like with the other ones. We see that anxiety 1, 5.2, anxiety 2, 3.9, and then anxiety 3 right there, 2.8. Back to what I was talking about, the idea of putting each participant, having each one of their DVs in rows instead of columns, reshaping it, what they call from a wide to a long format. So yeah, this is how I do that DV. Now we're changing our data frame to this DV long is where we're going to look, and we are pivoting basically how they are from the columns into the rows. Now, so this is how it was: anxiety 1, anxiety 2, anxiety 3. Now we have anxiety 1, 2, and 3 for subject 1, 1, 1. So each one for subject, each person's going to have 3 now instead of having those 3 different columns: anxiety 1, 2, and 3. So for participant 1, at the first one, it was at 7. At the second one, it was at 4. And then the third one, it was at 1. We also have to make sure that R knows that this is our factor, the different anxieties there. So anxiety 1, anxiety 2, and anxiety 3, that's our factor. And then we run the repeated measures ANOVA. I've pulled up one of those libraries for this. Let's see what it looked like in SPSS. Okay, in SPSS, we do have a significant ANOVA. We go to our tests of within subjects effects. 2 and 28 are F10, less than 0.001, partial eta squared, 0.42. And you can see that right. Time, our degrees of freedom, 2 and 28. Some squares are F 10.19, like in SPSS. Our p-value, it's pretty small. So again, it's that exponent, you'd have to move the decimal place over 4 times. So p less than 0.001. There's some other information there if you want to look at that, but just quickly trying to get through this. We could do the mean difference between each group, diff 1 to 2, the difference between 1 and 3, the difference between 2 and 3. We're just taking the means from each one of those variables minus each other. So it looks like from 1 to 2, 1.27. It's like maybe this is the one that's going to be the most significant. 1 to 3, the thing that's driving this ANOVA. And so we can do these pairwise comparisons. In this case, I'm using the Bonferroni, just like with the last one. If we print that out, let's see what we have. And that's exactly right. So anxiety 1 to anxiety 2, the p-value is 0.14. Not significant, but it's anxiety 1 to anxiety 3, p less than 0.001. And that is that mean difference of 2.4 from the one right up above there. We can get our eta squared as well. It's a calculation. And so let's see here. Our eta squared was our eta squared was 0.421. Okay, and then to get the partial eta squared, for some reason it has some difficulties calculating this. It doesn't just automatically show up. And so we actually have to calculate that. And so we go to our ANOVA table and get the sum of squares for the effect and sum of squares for the error from those tables. And then we can then we can update that table and view it with the partial eta squared. So if we come down here, if we come to the second part for time, that's our factor. If we scroll over here, 4.21, which is what we had in SPSS. Okay, again, I'll post this video and then I'll post this sheet so that you can go and pull this up anytime you want to. Also post this sheet with all of our APA write-ups so that you can come back and if you need a refresher again or just kind of getting started with R, but it's not as difficult as people would like to think. And just kind of as an example, especially nowadays, it's much easier because of things like ChatGPT or Claude. So I was having some issues getting that partial eta squared, and I went to ChatGPT and it comes up no problem. How do I conduct a one-way ANOVA in R? And I mean, it's not perfect. So ChatGPT, at least I've used it more with this. I've used Claude more for other things, but ChatGPT is not perfect, so don't take its word as law. For example, one time I had it do a correlation and it reported the degrees of freedom as the n instead of actually the degrees of freedom. So there's some it hasn't been trained quite properly on some of these things yet. In any case, if you do that, how do I conduct a one-way ANOVA in R? The data frame, just like we were talking about, our factor running, I mean, it's exactly the same. The summary tells you what it is, how you can plot it, the 2 keys, all that stuff. And so I know it seems for some people who have never done this kind of stuff that R may seem daunting, but if you use some of the tools out there that are available, it's not that much more difficult than SPSS was, and some things are actually even better. Okay, I hope you find that useful, and it will definitely help you throughout this course. All right, thank you very much for listening.